Max and I would like to present our undergraduate thesis entitled U.S. Coast Guard Cutter Lilac Feasibility Study, Electrical Renovation of a Historic Lighthouse Tender for Passenger Service. First, for a few acknowledgements. First, to our principal advisor, Professor Bradley Golden, for his expertise and guidance through this process. Next, to our reader, Professor Michael Martin, for his technical expertise in electrical engineering, as well as rating our thesis. Next, to our editor, Professor Richard Harris, for editing our thesis, and to the Lilac Preservation Project, including Mary, Angus, Luke, and Tim, for inviting us on board their vessel and providing us with data. For a brief outline, Max and I will discuss the vessel's history, the objectives of our work, previous work done with the Lilac, background and theory, and our procedure, which includes the power plant sizing, the development of an electric plant load analysis, the development of a one-line diagram, and the machinery layout used to show a proof of concept. Then we will provide some conclusions and recommendations for future work. The U.S. Coast Guard Cutter Lilac was built by Pusey and Jones in 1933. Then she served as a lighthouse tender from 1933 to 1972 in the U.S. Coast Guard. As lighthouses at the time were not automized, they needed to be supplied. This ship is now more akin to a buoy tender rather than a lighthouse tender. She also, during World War II, served a brief stint in the Navy. The Lilac also served as a trading vessel from 1972 to 1984 before she was moored in the James River. In 2003, the Lilac Preservation Project acquired her and moored her at Pier 25, where she serves as a museum ship today. The Lilac Preservation Project is a nonprofit organization with 3 goals. First, to restore Lilac and upgrade her for passenger vessel service. Next, to promote the ship's historical significance. And lastly, to earn revenue for her continued maintenance and operation. Currently, this is done through stakeholders, but the Lilac Preservation Project would like for her to act on her own will rather than through the benefactors that currently supply the money. The objectives of our work include to develop a plan to overhaul Lilac's electrical system in accordance with the Title 46 of the Code of Federal Regulations, and to propose modifications while preserving her historical integrity. Previous work done on the project was done by Ian Cossack and Cross Weeks in 2021. They conducted a feasibility study for the Lilac stability, which included an inclining experiment, as well as subdivision recommendations. Cole Mathis also completed his C-term aboard Lilac and provided drawings that aided in our thesis. The U.S. Coast Guard Cutter Lilac is America's only surviving steam-powered lighthouse tender. She was 174 feet long, had a beam of 32 feet, and had a cruising speed of 11 knots. Her propulsion arrangement is as follows. She is twin screw and direct drive, driven by 2 triple expansion steam engines that were driven by 2 Babcock and Wilcox water tube boilers. They are currently inoperable, as when she was moored in the James River, rainwater accumulated in the boilers and rendered them useless. She also boasts a DC electrical system, which contains 2 Galt electrical generators and a degaussing generator that was added during World War II for her stint in the Navy. Since our thesis regards the electrical arrangement of the ship, we would like to spend a minute to talk about alternating current and direct current. There is a stark difference between the two, as AC current flows in alternating direction and DC current flows in a single direction. There are some advantages to both with respect to shipbuilding. Some benefits of AC power include there is an increased efficiency in power transmission over major distances without major losses. You have the ability to step up and step down voltages quite easily, and it is cheaper overall. Next, DC power has better voltage regulation, more consistent power, and simpler wiring. The Code of Federal Regulations, Title 46, governs shipping within the United States. For the purposes of our thesis, Lilac is governed under Subchapter T, which means she will be designed to the standards of a small passenger vessel under 100 gross tons. She will hold up to 150 passengers, and she'll have overnight accommodations for less than 50 passengers. The current condition of the Lilac's electrical system is quite bleak. Her original DC power plant has been heavily modified, and each time it was modified, it decreased the quality of the electrical wiring. In 1942, Lilac was armed and outfitted for World War II, As discussed earlier, a degaussing generator was added for her stint in the Navy. In 1962, there was also the addition of an AC system, which included a 15 kilowatt Hercules-driven engine generator. Also, there were various additional modifications during restoration, although the 1962 configuration is what we see largely today. In 2012, she was outfitted with an auxiliary generator that provided power, while Pier 25 did not have power after Superstorm Sandy. From our visits to the Lilac, we believe that the current electrical arrangement is temporary and does not meet a marine working standard. This is because there are exposed wire runs, incorrect wiring of load centers, and an open-face DC switchboard, which is still live and hazardous. Therefore, we believe it is important to redesign the electrical system to meet these modern requirements, which includes the design of a new AC system, as well as accounting for additional hotel and engineering loads. The current condition of the inboard profile behind me shows the 6 switchboards that are on board the vessel today. I would like to highlight one of them, this being the open-face DC switchboard that I was talking about earlier. It is important to the Lilac that we keep this as a museum piece, even if it is not functional. Now we ask the question, how do we repower the Lilac if her boilers do not work? Do we cut the shafts and make her diesel driven? Do we use a modern boiler substitute akin to what she has today? Or do we produce steam using electricity? Keeping in mind that the Lilac Preservation Project wants to have a functional steam system on board the ship, the first option was eliminated because it does not maintain the historical significance of the ship. The second was also nixed because we do not believe an oil-fired boiler will stand the test of time with respect to environmental regulations. Therefore, we chose the third option, to generate steam using electricity. Therefore, a conversion from the original system to an electrical steam generation system would be needed to be designed. The original plant is as follows. An oil-fired steam boiler produced steam, which provided power for propulsion and auxiliaries through the use of direct steam. And then steam was used to turn generators that produces power for the house loads. Sorry, someone just joined. Since the operating profile of the Lilac has changed, it is important to eliminate the loads that are no longer there, such as the working crane, because she will not be bringing buoys on board. Also, since the role of steam has changed in power generation, we do not need steam-driven DC generators, so therefore this can be eliminated from the power production of the steam boilers. The new plant is as follows. We have a diesel generator providing power to the electric steam generation, which is an electric steam boiler for propulsion and the remaining auxiliaries, and then to the electrical loads, which are engineering loads, hotel loads, and museum loads. This provides an interesting aspect of our thesis, which we can use to future-proof the vessel a little bit. As battery or fuel cell technology increases, we can swap the diesel generators for a greener form of electricity. To size the boiler, basically we need to know the new boiler steam capacity. The Babcock and Wilcox boilers had a max duty cycle of 12,500 pounds mass of steam each per hour at an operating pressure of 200 PSI, which was saturated steam because at the time this was the cheapest and most effective option for running a boiler. These were oversized, and one of these boilers could easily hold the steam capacity or the steam needs of the ship. Then we need to subtract out the demands of the crane hoist engine and the DC steam generators to arrive at the new boiler size. The crane hoist engine on board has no nameplate data. We do know it was made by Lidgerwood, and we do know that it has a max working load of 20 long tons. The Lidgerwood bulletin number 11 was used because it was the same company and had multiple different crane hoist engines, although not at the specification that we required. We require 20 long tons. Therefore, regressions between power, working load, cylinder dimensions, and drum dimensions were used to arrive at a power estimate. Our power estimate is 170 horsepower. The DC generators on board had a power output of 20 kilowatts or 27 horsepower each. Using the equation power equals pressure times stroke length times cylinder area times rotational speed, we arrived at an indicated power of 73 horsepower each, keeping in mind that the efficiency of generators has increased greatly since these were built, which leaves the remaining steam loads for the propulsion, the windlass, steering engine, the miscellaneous pumps, and auxiliary steam. Therefore, we could size a boiler. And for that, I will introduce my thesis partner, Max Ma, to present the rest of our thesis.
Thank you, Joe. Now that we know the power required to power the remaining loads driven off of steam, we can size an electric steam generator. For this, we went with the Bosch Electric Steam Boiler Unit, or the ELSB. This unit supplies high-pressure saturated steam, and the selected unit that we chose was the ELSB5 due to its parameters falling within the range of what we require. The boiler capacity or power is 3,400 kilowatts with a steam flow rate of 11,000 pounds mass per hour, supplying pressures of up to 350 psi. Its dimensions are shown here for context, and we will discuss the machinery arrangement in detail later, but it's approximately 16 feet long, 8 feet wide, and 9 feet tall. While designing the entire new steam system was outside the scope of this thesis, it's important to note that Bosch manufactures additional modules, such as a water treatment module and a condensate management module, which are important to complete the loop of a new system. For the purposes of our EPOA, conservative estimates for each one of these units were added. So as Joe mentioned before, there are two pieces into redesigning the electrical system for Lilac. There's sizing the boiler, which is the major propulsive load, and then also taking into account the remaining loads that are driven on board the ship, as well as additional loads shown needed as a passenger vessel. For this, we introduced the electric plant load analysis, or EPLA. An EPLA is an organized master equipment list. It's analogous to a financial balance sheet in which the sum of all the assets in one column has to equal the sum of the liabilities. Therefore, here, we see the power requirements of all electric power consuming devices has to be balanced out by the power plant that we sized. Electric power consuming devices are grouped by load category and by operating condition. And functional operating loads for each of these operating conditions are specified in the EPOA. It's important to delineate the difference between rated loads, which are typically found on nameplate data, and also load factors, which are percent usage cases for how much that load is used in said operating condition. The end goal of an EPOA is to determine the required generator sizing and configuration. The EPOA was developed by conducting several vessel survey visits on board the Lilac, in which we inventoried existing loads in each space and also kept in mind what additional loads we anticipate. Major load categories included the following. First, hotel loads, such as potable water, sewage, heating, ventilation, and air conditioning, refrigeration, lighting, various appliances, and galley loads. Museum loads, such as interactive computer displays, exhibits, and also power tools needed in the restoration process. Classic engineering loads on board every ship, such as fuel system, bilge and ballast, fire, and compressed air. And finally, navigation needs, such as lighting, PA system, gyro compass, radar, and depth sounder. Loads were estimated by first checking the requirements within 46 CFR Subchapter T. For example, though we did not have detailed piping system data, we were able to perform basic calculations to size pumps based off of what we knew. And once we knew what was in the ballpark, then we're able to make good estimates. We also conducted research for the vessel's remaining loads that were on board and things that we needed, additional loads we needed to find out. Load cases were developed by using two major documents. The first was a Coast Guard document called Navigation and Vessel Inspection Circular number 2-89, and the second being a NAVC document, Design Data Sheet 310-1. Both of these were used to find load factors, and when We couldn't find anything from these two documents. We resorted to EPOAs of similar size vessels to find what we needed. And with this, we were able to size the power source for our arrangement. Shown here is a section of our EPOA, which I'll discuss in further detail. As you can see, it's arranged by focusing on one specific space, the upper level and the pilot house. Every load occupies its own row, and we have the quantity, rated load, and total connected load shown in the highlighted box above. 3 operating conditions were identified that the Lilac would need, such as while inshore, cruising, and an emergency load condition. So let's break this down a little bit further. We'll take an example load, such as the electronic chart display and information system, or ECDIS. There's one of these loads, and its rated load is 0.3 kilowatts, and therefore its total connected load is simply the quantity multiplied by the rated load, which is the same 0.3 kilowatts. In each one of the operating conditions, however, it has a different load factor, which is important to note. While inshore, this equipment is not needed, so the load factor is 0. Therefore, the power drawn in this condition for at shore is 0. While cruising and while in the emergency condition, the load factor is 0.6, or 60% of the total use case. Therefore, this number is multiplied through by the total connected load to acquire the load in the cruising and emergency conditions of 0.18 kilowatts. With the EPOA complete and all the loads sized, you sum through in each operating condition, which yields the total projected loads in each condition. In the cruising condition, we see that the Lilac requires 3,430 kilowatts, with the shore power and emergency conditions requiring significantly less power at 9 kilowatts and 7.5 kilowatts respectively. With this, we were able to size our power plant. We selected 2 MAN 175D gensets in order to supply sufficient power in the most demanding operating condition, the cruising load of 3,430 kilowatts as mentioned before. So we see here that this unit is diesel electric at light duty. We selected the 12-cylinder V-line configuration. Its maximum continuous rating is 2,280 kilowatts, and it supplies a rated electrical output of nearly 2,200 electric kilowatts. The layout is pretty standard of generators, with the engine and alternator being connected through a single bell housing, which is resiliently seated on a base frame. It's also important to note that key engine-driven systems, such as a modular common fuel injection system, a lube oil system, and also a cooling system, are driven directly off the engine, and therefore do not need to be considered as separate loads within the EPLA. Next, I'll move on to discuss the one-line diagram. A one-line diagram shows power flow in an electrical system from sources to loads. It's essentially the electrical engineer's roadmap to seeing a simplified arrangement of how power moves without the complicated wiring. There are 3 major elements to a one-line diagram. There are sources, which include generators, shore power, and possibly batteries. Loads, such as motors, lights, and fans, compressors, as well as distribution equipment, such as switchboards, transformers, power panels, cable, and circuit breakers. The one line indicates ratings of equipment on board and also aids with troubleshooting and helps to ensure redundancy throughout the system. The strategy for outlining our one-line diagram is as follows. We delineated load centers from our general arrangement and the EPLA, which loads, for example, were concentrated in each space of the vessel. Furthermore, loads were arranged by their voltage rating and associated bus that they would be connected to, with special considerations being made for the emergency switchboard, containing key loads that you would need to get out of a jam, such as navigation lights, a general alarm, bilge and ballast pumps, and a fire main, as well as an important delineation for how power is transferred to shore power. Also, to note, distribution equipment such as transformers, circuit breakers, and rectifiers are included in here to show how power is distributed and converted. As Joe mentioned earlier, in the fall semester, we conducted visits to Lilac to assess the existing configuration of the electrical system. So shown above here is a simplified arrangement of the one-line diagram that exists on board today. We see that shore power is supplied at 3-phase 220 volts of AC power to a main distribution panel. This feeds 4 remaining panels located in the lower engine room, the ward room, the pilot house, and the crew quarters area. Also, as noted previously, a rectifier provides 115 volts of DC power to the DC switchboard. Shown here is a simplified arrangement for our proposed new one-line diagram. As you can see, at the top, we have the major sources, the same three-phase 220 volts of AC supplied by shore power, the pair of man gensets, as well as an emergency diesel generator. Distribution is shown by 5 major buses, the main bus at 220 volts, the steam system bus at 400/690 volts. That's just the difference between the phase-to-phase voltage and also the line voltage. The 120 volt bus, an emergency bus, as well as a smaller DC bus to handle those smaller loads that run off direct current. So as mentioned before, at the very bottom, we have the loads. Shown on the very left are the steam loads that require the most power and also run at a higher voltage. So this includes the ELSB, as well as the additional modules such as the condensate and water treatment module. On the 120 volt bus, we have auxiliary loads, most of which run at that voltage. This includes galley equipment, auxiliary machinery, and also museum displays and loads. On the emergency bus, we have loads such as fire pumps, bilge pumps, and on the DC bus, things like emergency lighting, navigational lighting, as well as the PA system and the general alarm, which are already installed on board. We went back and forth a little bit about the options for emergency power, and the two options being battery backup or just maintaining a classical diesel generator. There are advantages to both. The advantages of battery backup are, of course, that it's essentially a cleaner form of energy. There's power readily available, and if needed, continuous power charging while underway through the diesel generators to the batteries is possible in a hybrid arrangement. However, at this time, we've designed the system as it's in place, and this could be extrapolated to future work, as well as the fact that the advantages of a diesel generator far outweigh that of having batteries at this time due to simplicity and cost. As Joe mentioned, the Lilac already has an emergency diesel generator which can handle the required power needed in that condition that was installed during Superstorm Sandy. With the EPLA one line complete and all equipment spec'd out, it's important to see that this arrangement is physical by looking at a machinery space layout of what existed previously and our proposed new arrangement. So shown here is an inboard profile of the machinery spaces. We see the lower engine room takes up a length of approximately 27 feet. The boiler room takes up about 22 feet by 11.5 feet tall. The original boiler dimensions are shown on the right for context. And there are also upper sections to the boiler room and the upper engine room, which are shown. Here in this arrangement, we've substituted out the original Babcock and Wilcox boilers with the ELSB5. The new boiler dimensions are reiterated and compared on the right for you to see. Now we'll also look at an overlay of the plan views. So originally, these steam spaces are looked at from the tank top level at an average beam of about 30 feet. So just explaining out what each little one of these boxes is talking about. We have the steering engine located aft, the condenser, the pair of triple expansion engines, and also the Babcock and Wilcox boilers. Now what we've done with the new arrangement, we've removed the original shell and tube condenser, and we'll replace it with a modern equivalent. And also we've placed the ELSB5 and 2 MAN 175D gensets within the space. Adequate tolerances are shown, although it's a little tight. Another arrangement could be to move the gensets up to the cargo space and maintain more spaces on the wings of the boiler room and also in the engine room for the additional modules that are supplied by Bosch for the steam system. Genset dimensions are reiterated here again for context. The conclusions of our work are the following: that we were able to conduct a concept to preliminary level electrical system design that is feasible for the Lilac Preservation Project. We learned a lot that was not really outlined here in this presentation today. There's significant challenges in dealing with a ship that's 100 years old and managing a stakeholder project. And as you can probably tell, the system that we selected was probably far from the cheapest and far from the most efficient, but it maintains their wish of maintaining steam on board. Our recommendations for future work are as follows. First, a major piece of marine engineering, which is necessary, would be detailed piping system design for the major fluid transport systems. I'm talking about potable water, sewage, and the fire main to actually spec out the pipe size so that the ship can actually operate. A resistance and powering analysis for a ship this old could be interesting, whereas Joe and I looked at how much the original boilers were rated at and subtracted out loads that were no longer needed. This problem could be approached from the opposite end. An indicator diagram could be constructed for the triple expansion steam engines, and shaft loss calculations and resistance code could be used to construct a speed power curve to see how much power would actually be required to push her at her design speed of 11 knots. Finally, detailed design of the electrical system would be needed, such as more accurate load specifications, zeroing in on that design spiral, as you heard from Conrad and Darren, and also cable sizing and procedure recommendations for the installation and detailed drawings for this system. Thank you very much for listening to our presentation. I'll now invite Joe back up, as well as Conrad and Darren, to answer any questions you may have.